Hello everybody and welcome to Heat Transfer. Here we have a system of two similar airfoils that are in different speed and temperatures, well different speeds of airfoiling over them. This one's at 100 meters per second is the air moving across it, and this one has a velocity of 20 meters per second moving across it. Each one of them has a surface temperature at 400 K and the air is always at 300 K. We know that for object number 1, the heat flux is 20,000 watts per meter squared. And it's atmospheric air. This one is 5 meters long and this is 1 meter long. So if you can't read that, hopefully it's clear now. So we're trying to find the convection coefficient for object number 2 with the velocity that's listed up here. So pause the video and take a screenshot of this if you need a picture. Otherwise, just copy it down. We'll move ahead and you won't be able to see it again here for a minute. Alright, so working with this problem, first thing we want to do is kind of establish our base parameters. So I'm going to go ahead and look at air using, in my book, it's table A4, and I use the Incomplete heat and mass transfer book. So we have a viscosity. Viscosity is equal to 15.89 times 10 to the negative 6 meters squared per second. And this is at a temperature T equal to 300 Kelvin. And it's the same for both of them, so we only have to do this one, which is nice. And then K is equal to 0.2263 watts per meter Kelvin. And then alpha is equal to 22.5 times 10 to the negative 7th meters squared per second. And then the Prusset number is equal to 0.71. Okay, so we're looking for a heat coefficient. So with these, we have air flowing over a thing, so we're probably going to need to use Reynolds number and probably even Nusselt number. So Reynolds number is going to be V1L over viscosity of 1. We'll say 1 for now. And then Nusselt number, average, is going to equal H average over L times KF. Now this L is actually the L of these two objects right here, so the total length of each one of them. Despite their geometry, you just use the L. Okay, so if we look at number 1 first, the very first object, we're going to establish some parameters here and try to figure out an extra variable or two. We're going to look at R1 is equal to B1, which is 100 meters per second, times 1 meter, which is its length, all over 15.89. Let me get this up so you can see it. Times 10 to the negative 6 meters squared per second. And if you solve this out, you get over 100 over 15.89 times 10 to the negative 6. And the reason I'm just leaving it like this is because I want to make a point here or something. I'm going to go ahead and look at number 2 now, just real quick. Reynolds number for number 2 is equal to 20 meters per second times 5 all over 15.89 times 10 to the negative 6 meters squared per second. 0.89 meters squared per second. And look at that, this is going to be equal to 100 over 15.89 times 10 to the negative 6. So you see this direct proportional relationship between length and the velocity. So long as the length and the velocity multiply to be the same value, Reynolds number of the two objects is always going to be the same thing. So you can pretty much ignore the bottom part so long as temperature is constant for both of them, which it is in this case. So the properties don't change at all. It's just the exterior circumstances, basically. Okay, so if Reynolds numbers are the same, R1 is equal to R2, then the Nusselt numbers also have to be the same. So NU1 is equal to NU2, average. Always look at the average Nusselt number. The local isn't really used very often. So if we take each one of these now, we have H bar L1 over K is equal to H2 bar L2 bar, oops, not L2 bar, just L2, over K. Now we're looking for the heat transfer coefficient of object 2, which is right here. So these two will cancel, and we'll get H1 bar L1 over L2, which is equal to H2 bar. Okay, cool. So now we have an equation for finding the heat transfer coefficient, just using Reynolds number and Nusselt numbers. But how do we get this H bar? Well, usually whenever you're looking for h bar in a flow problem in thermo, or heat transfer, you use the equation Q is equal to h bar A times Ts minus T infinity. And now if we just solve this out, we have h bar is equal to Q all over A of Ts minus T infinity. So that's pretty handy. And if you look at this, this is Q over A, which would which will basically make this this would be equivalent to Q flux over Ts minus T infinity. Just like that. Wait a second, I may have made an error there. Yeah, because Q is equal to Q double prime over A. So Q over A is going to equal Q flux right there. This is the relationship that we're looking at to get to this point, to make this leap. So Q divided by A is equal to Q flux. And we have Q flux given to us earlier in the problem, right here. So now, what we can do is set this one up for H1, set this equal to H1 bar, just like this. And if we solve that, then we'll get H2 bar is equal to L1 over L2 times Q flux Ts minus T infinity. And the surface and the T infinity are the same for both of them, but this would actually be a relation of 1. So we'll say Q1 and 1, just like that. So it's clear. And if you do this, then you have L1 is 1, 5, all over 20,000 watts per meter squared, all over 400 Kelvin minus 300 Kelvin. And solving this out, you get, oh, sorry, okay, the pencil doesn't want to work. H2 bar is going to equal 40 watts per meter squared Kelvin. And that's your answer. So it's pretty easy. You just use the Reynolds number to prove that you can use the Nusselt number, that they are related. And then you use that equation, since it has the h bar that you're looking for in it. You solve for h bar. And then in order to find the h bar with relation to something else, h bar of the original one for which you have a heat flux, you use the very basic heat transfer equation right here to get this into a form where you can solve for H2 using the variables you have. So pretty easy.